Hello again. Actually, I don't feel quite ready or fresh enough to do math, but I really wanted to do some, so let's see if I can handle it. Simplify the expression for the x-coordinate of 2p in case of an elliptic curve of this form. So it's y squared equals ax to the third bx squared cx d. So a equals unity and c minus n squared. So we take the formula 7,2 and reduce it. Let's call it x2 instead. Minus 2x plus naught plus the derivative, that's 3x squared minus n squared divided by, that has to be squared, divided by 4y squared and y squared equals x to the third minus n squared x. So we have to put them on with the same denominator. Minus 8x squared and we need to check if that's right. Minus 4x squared, x squared minus n squared, and I think that's right. So we expand the numerator. And this gives x to the fourth plus 2. Plus n to the fourth x squared plus n squared squared divided by 4x it's minus n squared, so no reduction is possible here. Right. On the other hand, this is y squared, isn't it? That's 4y squared. I don't know if that's better. One of those two. That was A. Now, you see, reading this, I realized that I couldn't go unprepared into doing this. So I found those formulas. This is the point from the paragraph itself, and this is the point from the exercise. And to check it, I took the 3, 4, 5 triangle and the 2 points. I do, of course, remember the last one, but not the first one. And I also checked with the other one. I like this point better, really. Oops. Here we have Krita. Now, if P equals 2Q, then these points are on opposite sides of the x-axis. So I should think that the 2 times it were on the opposite side. So that's a little odd. So maybe we should just test to see what twice this, and one of them will probably give the right one, and the other not. But why is that? So we have to show that, oh my God, I should have written the formulas here so that I could write out twice the... Let's take the x value first, because that's what we need. And we have that here. X squared plus n squared squared. Squared divided by 4y. Squared, 4y. What? And then there's enter the value for x, which was minus xy squared divided by 2x plus z and n squared divided by 4y which equals x squared minus x minus y squared times z eighth. So, well, I think I just gotta do it. You know what, this is really terrible. I think it should be done on Maple. I can't help making mistakes when I'm recording what I'm doing. Oops, I shouldn't have finished the parentheses there. What? There we go. Squared plus I think I can do that. Squared divided by 4. Let's say 1/2. So what do we get here? I need to make it a slightly bigger. So I'm looking for a reduction using that x squared plus y squared equals z squared. Maybe Mabel has a method. No, it doesn't. That really helped not at all. Well, we have to show that it equals the other point, by the way, so maybe everything's not lost. And that point is on the other Maple screen. So it now look at this. I used the y value. So of course things should go terribly wrong. So we'll just go backwards here. Now, x, that was set half. Oh, now what was it? Oh, it's on the Maple screen, yeah. It's set squared divided by 4. Z squared, that sets the 4 divided by 4, that is 16. I'll just check it again. Z squared divided by 4. Squared, 6, 4, 16, plus and this has to be squared divided by 4, and y, that was the one times what? Times z. So we take 16 out, let's write it as 16 squared. And z to the 8th plus x. Oh, we get 6. So now this is difficult. If we take it out, then it's 4 here. No, if we take 1/16 out, it's 4 here. So double the product is 8. And 16. So the total, the order of each nomial here is 8, all right. So what can we do here? Well, we should look at what we need to reduce it to. we need to reduce it to x y squared That's quite a reduction. That's really a reduction. Maybe we should just eliminate z up here. So now we have to square this guy. So the double product of the first two is 4. And then we get the double product of this times this squared. That's 6. Oh, I could have used the binomial formula, of course. Right. And then, so this is one of them, and then this one, now what is this, times, so first x to the 4th, then 2x squared is 16, and y to the 4th, sixth. There we go. And then this one we can let it stay. So let's see what we get. The numerator. X to the 8th. And then x to the 6th, that's 12. And 4th, it's 16, and 6, that's 22, that's 38. And then x to the 2nd, 4 and 8, that's 12. It's symmetric, that's nice. And then finally x to the 8th. This doesn't look like anything I have any chance of handling. So, it turns out that my feeling was right. I wasn't really fit for this problem. I could solve problem A in case I got the right result. But the resources, my mental resources were just used up as it came to problem B. So I stop for today and then I'll take it up tomorrow. Right, back again. Unfortunately, the program or the computer stopped. I don't know exactly what happened. I know how I did it though. I wanted to move the webcam a little before restarting the video. And then it, for a millisecond, disconnected. And then when it was online again, it didn't work with the voco screen. So I don't know what happened, but now I rebooted without the webcam and then inserted the webcam, and I hope we are ready to run. Now, what do we have here? We needed to show we needed to compute 2q. That was our point. And the x value, that is n squared plus the x value squared, n squared t squared, divided by 2y. And then up here we get z. And all this should be squared. Now, 1 plus t squared, oh, that will cancel, how nice. So it's n squared times z, and 1 plus t squared, we get from here cancel with this, divided by 2n squared. So that's z half squared. That was, as far as I remember, exactly the x value. I just need to check the Maple file again. So that's p z squared fourth, right. It just occurs to me now that you can see the date up here, February 12th. So you can also see the time, so you can check that how long time my lunch took. That must be nice to know. Now for the y value, I've been using the formula from the formula 7.3 all the way through, so no reduction there. So it's minus y plus m times y minus the new x. So it's minus 2y, isn't it? No, that was, it's minus y, all right. So we need to compute m. I believe I've done that before, haven't I? I didn't write it explicitly at least, so we'll do it again. It's the derivative 3x squared minus n squared divided by 2, and then the y value. So we'll just put that in. And x1, that's n squared t squared. And this should be multiplied by the y value. So let's just write y down here. Y, and that's the new y value, minus the new x value, this is the original. Oh yeah, that's because it will cancel part of it. Then when we multiply by I, we get 3/2 n squared t squared minus 3/2 n squared. And then this guy, minus and then times z, and times z to the second, that's z to the third, divided by 8. My God, where will this end? And this is z. This is z. Oh, these guys cancel. Not that that helps me much. Well, let's check what it needed to, where we need it to end. Maybe that will help me find a way. X squared minus y squared times z eighth. Was it times z divided by 8? Yes. So we need to eliminate t, and we have t here. So t plus 1 as x plus y plus z plus y divided by x plus z. Oh, t squared. We'll just do that. Is any luck going this way? X squared plus y squared gives z squared. It's 2z squares plus xz. And down here we get, now that's interesting. Let's try. X squared plus y squared gives z squared. So we get 2z squared plus 2xz divided by x plus z squared equals 2z. So we get z plus x divided by x plus z. So that's this guy. This gives 2z divided by x plus z minus n squared times 2 divided by x plus z. All right. And we have this guy. Oh, it's 3/2 n squared, t squared minus 1. So that y squared divided by x plus z squared minus x plus z squared equals, now we want to get rid of y, so we write that as z squared minus x squared, so z squared goes out, so it's minus 2xz minus, now what was it that cancelled? It's interesting. I usually have a band slope running around where the last sentence I've said is still available. But this time I was thinking so deeply that what I just said wasn't available. So I'll just do it again. So we want y. We write that as z squared minus x squared. So it's minus 2x squared. So we get here x plus z minus 2x. It's very annoying that I don't seem to be able to correct this. Then I still have this. I wish I knew how to change that. And I can't change back. So it happens when I'm down here. Oh, so it's just a matter of... I see. All right. Now that was actually a good thing to learn, that I have a lot of space down there. All right. So let's just check it. This gives z squared eats that one, so it's minus 2x squared minus or plus the double product. So it's minus 2x divided by z plus x. So it should be a minus up here. Oh, let's write it x plus z. Right. So the last term here, I did notice that n squared cancelled. So it's 3t squared minus 1 divided by 1 plus t squared. I have a feeling that there's a much quicker way to do this. But I just have trod along the path that I once did choose. So it appears that we must compute 3t squared minus 1. So I'll just do it very, very slowly. That was y divided by x plus z. Yes. Denominator, sorry. So, don't you think we should get rid of y? Three x to the second and 3z. It's z to the second minus 3x to the second. Not sure that's a good idea. And if we do x as z squared, so we don't get a complete square, whatever I do. So I believe the right thing is to why am I eliminating y? The final result should hold a y squared and a z, but that comes from there, that comes from there, so let's try to eliminate y and see where it leads us. I can't see anything working better, though I can't see this working anyway. Now, y is, so it's 3, we'll just get rid of all this. So it's 3z squared, that gives 2z squared. And then minus x squared, so that's minus 4x squared. Squared, Miller. There we go. Now, if we eliminating x and z makes no sense at all. So that was minus that was the one down here. No, that was 3t squared minus 1. So we divide it by 1 plus t, so we'll just do that. So that's dividing by z and multiplying by x plus z, and then a factor 2 being removed from the top. Interesting. So that was 2x plus z, and then a z, we get down here. And that has to be multiplied by z eighth, so it's a z squared eighth. And that was a minus, so we change sign. Plus two z squared, 2x squared, plus xz minus z squared divided by x plus z What about the factor 2, by the way? There's a factor 2 there, which eats this factor 2, and here's another factor 2, that's a factor 4 in the denominator. One of them is eaten going down here. I'll just check this. 3, that one, and 1 plus t squared 2z divided. So this is the right one, and then we have to divide it by 2 and by z to the third x, the z to the second 16th. Z squared 16th. That 16 does feel a little wrong, but it's like it's here from the beginning, so I just got to believe it. Well, let's get on a little. So n squared is not here. X plus z is common denominator. That's good. I've been wondering about how to check the dimension of this result. I know it's a physicist's term, but then the height in of some ring, each expression being added should have the same height. So that would make it easy to find an error. So you're probably seeing me doing some very by far too complex algebra to get a real simple result. Of course, not quite simple, but it's not like extremely complicated. So I think I'm overcomplicating stuff. I don't know how, though. So I've come to the point where I'll take another break, have some water, of course, and then I'll try to go through it all and trying to find the the dimensions of each term and see if any of these have gone wrong. And then we'll take it from there. So I'm back. I've thought a little about dimensions here. Now, if we put x, y, and z to have dimension L, then n, which is half xy, has dimension L squared, and t being y divided by x plus z is a scalar. And when we go to x on the elliptic curve, I think we're down here, it was minus nt, as an example. And then y must be here, and that's hopefully it must be here because y squared equals x times x squared minus n squared. So that's 2 and 4, that's 6, L to the 6th. So y squared must be L to the 6th, so y itself to the 3rd. Now we did have a formula for y here. X, this is dimension 2, dimension 3. So then I've been thinking, what lies actually behind this dimensional analysis? In the book, it's called weight, when considering the power of z in the lattice sums. So, but it's actually the same phenomenon that goes on, and that means that there is something that I don't really get here. Why do we have different units in physics, and what's behind it? Now, while I was making coffee, I thought about this, and I got an idea that it was because of an underlying symmetry. If we look at this, then x, y, z, they are distances in a plane, and they may be scaled by choosing another unit of measuring length. And they must all be scaled together, particularly if we want to have the different directions, then scaling one direction must scale the other direction similar way. So if we now say that the symmetry is that all lengths are scaled by one parameter, then what scaling do the other entities have? T, now it's scaled by, say, multiplying by alpha to the first, then t is multiplied by alpha to the second, no, to the naught. The area is scaled as alpha to the second, and of course the same way. So maybe it's just a question of a symmetry, an underlying symmetry that we are using. So maybe units are basically the result of an underlying symmetry. Now, that's all I'll go into this at this point, because I haven't any more thoughts of it on it really. I have just some vague ideas. So let's go back to the expression I have here. Now, y, that was L to the third. So this is L to the fourth divided by L to the third. This is nothing, this is L to the fourth. So this is erroneous. Yeah. And this is actually L to the third. So that means that this expression is dubious. And that was also where I stopped the first time, wasn't it? I haven't seen the video, so I don't know if I stopped here feeling there's something odd going on. So I hope I have some feeling for the underlying symmetries so that I will discover when things are odd. Now let's then check this guy. N to the squares t. Nope. Whereas this one, n to the n squared times z to the third. That's no, that's just z to the third, so they're okay. So y is to the third, and this is to the second. This is no good. Did I subtract the x value? This is, of course, the x value. So m has dimension length. Where did I compute m? And this is to the second, so that gives to the third as it should, yes. Now, so this is the only one that's wrong, so we just delete it. And it's the, so this is m, so this needs to be the original x value, which is minus nt. Now, why did we write y there? So we have to put in what y is. As they've done here. And then we multiply by nt. Oh, we can put n outside, so it's n to the third. So it's 3. Oh yeah, that was 3t squared minus 1 divided by, and then we have t, and we have 2n squared, 1 plus t squared, and the t and the n, that n was actually eaten, and so and then an n comes there. I will just do it better. So 3t squared minus 1, 2 eat, being right, and then I missed the z. Where did that go? Why did I do that? Oh, I guess it's a mistake. So let's check the dimension. This is dimensionless. Zn has height 3, height 1, height 2, 3 altogether, as it must. All right, now I believe this. I was just looking around to see if there was some obvious reduction in this parenthesis. That would be lovely, but I didn't see one. So we have to multiply by 4 here, and nt, that's xy, so we get y squared. Or maybe there is a reduction. I think I ought to do that, just to check. So we check. Oh, let's put an 8th outside. Then it's x, y, y divided by x plus z squared. 1, 2, 3, 2, 2, right. X, y squared plus x z squared plus z to the 3rd. Now what can we do here? I think we should get rid of y. So that's z squared minus x squared. I don't see that giving x plus z in the near future. If x equals z, if x equals z, then this guy vanishes. So we can actually divide that's a new one. I'll do it over here. I'm not good at making polynomial division, I must say. So it's z squared plus x to the third plus 2x z to the second minus x to the third. And we divide that by z plus x, and that should give z to the second that's an x. What? Oh yeah. No, it does, doesn't. If the division didn't go up, this gives, of course, x to the second. And when we multiply, then we get a remainder. So I was wrong. If z equals x, then these two cancel. Oh, if it's minus, if z equals minus x, no, then it does cancel. So what have I done wrong? This should be a plus. So it should be a plus down here. So this should be a minus. So it should be minus x squared and minus x squared, that's minus here. So the division does go up. So that means that it's z squared plus xz minus x squared. And z squared minus x squared, that equals y squared. So it's y squared plus xz. Okay, what was that? What was I actually doing here? Oh, that's the thing we multiply by. It could indeed be simplified. So instead of the nt here, we could just, we need a big one. I don't hope I'll be using that. Now, where are we? This is it, and then times x, no, let's do it black. No, let's do it blue, that's fine, then people can see where it comes from. Y squared plus xz divided by 8. And let's check dimension. 3, 4, 4, 6. 6. Now, this guy has dimension 3. No, it can't have, because this has dimension. This has dimension 2, and oh, there's a y down here. I missed this y. So this is just a number. So what about the z here? That comes from here. So this set, that's the 1. So it doesn't cancel. So Zn, that gives dimension 3. So if we just put a Z here, that's a bad color. Times this, then we have dimension 2, dimension 3. Oh, and then times n squared. Where does n squared come from? That cancelled, you see. So we let them cancel. So now we are so far out that I have no idea whether I'm really doing right or not. So we now have 8 down in the denominator, and this is a quarter x y squared, so that's a half, so it's 4, and times x plus z. So this is 4 x squared y squared, and 3 halves, minus 3 x z y x y squared z minus 3 x squared z squared This has dimension height 4, height 1, good. We have height 3. Oh, there was a Z here. Now, where do we have the expression I should end with? It was x squared minus y squared divided by what? Oh, here we have it. It's times z to the 8th. How can we get z to the 1st? If we take z out here, so we should be able to take z out. From nt. Oh, what happened to t, by the way? Did I totally forget about t? So, I think we've had this before, that doing algebra on the screen recording is very, very difficult. What I would usually do is to start on a new page where the other one is visible besides me. And I think that's a method that we really need to do. So what would be practical here was to have a printer so that I could print out a page, have it lying besides me while I was working on the other. But that wouldn't be totally practical because the visual distance, I'll have to move the eyes and then refocus all from beginning. So I don't have a landscape where things are nicely aligned, like I have when I'm working on some pieces of paper. So what I'll do now is I won't take a break, I'll just stop the video and then I'll do it on paper. And then I'll go back and then tell you what I've found out. So I'll take this as a lesson going forward, so that when there's some algebra that tends or seems to be or just threatens to be complicated and long, then I'll stop the video and work it out on paper and then present the result. It won't be what I really wanted to do, but it seems the challenge working on just one sheet being visible. If I had 3 screens, it would be difficult as well. So what I might have is have a very large screen and then divide it into 4 sections. Then I could do it, but I don't have such hardware. So I'll stop the video and stop recording or pause the recording, and then I'll come back when I've worked it through on. So I'm back, and as you can see, it's 4:45 in the afternoon. Have I started recording, by the way? Yeah. Now, I did go through the work as I said I would, and in the end I understood it so well that I could have Mabel do it, defining n and p and t, and we need not do that. Then 2p, and then simplifying with respect to Pythagoras' theorem, eliminating y squared. And that gives this result, and then I use Pythagoras' theorem again and factor it. If I don't factor it, then it makes a weird result. This. So it should put Z8 outside parentheses or whatever, do something to make it nice. But it's obviously that we have the y coordinate with the right sign. And I didn't doubt this expression, but I doubted, or I wanted to verify the sign. So the lesson of part B is that don't do it on a blackboard without preparation, because the algebra is not complicated, but it's sufficiently complicated that you can do it on paper. It's more difficult to do it by Mabel because you don't know which reductions you'll need when. So now let's get on to the final part of the problem. Problem C. If P is not a point of order 2, point of order 2, we'll just need a new one. The unit is the unique point at infinity. That's interesting. When it's the unique point, then it's the only intersection with the curve at infinity, x plus y plus naught. And that means that it, by Bezout's theorem, should be an intersection of order 3. Now if we put z on here to have the projective equation and then put z equal to naught, we get x to the third equals naught. So it is actually an intersection of order 3. That was a little strange to me because the linear function has an intersection of order 1, of course. The parabola y equals x squared has an intersection at infinity of order 2, and y equals z to the third has an intersection of order 3, but then why should y squared equals z to the third have not like order 3 halves, but it turns out it has an intersection of order 3 as well. That was contrary to my intuition. But that has got nothing to do with the problem anyway. So that was just a thought. Now, so the points of order 2, they're the points on the y-axis, and that has already been established in the text, because if you add them by themselves, then the tangent is vertical. So I needn't say much about that actually. And then from the first question, we have, it's not on here, we have the x value of 2p is x squared plus n squared divided by 2y. Oh, that's the minuscule y squared. So it's the square of a rational number. So we have to show that we will get an even denominator. Whatever x and y be. So, how can we do that? of course, n is square free, so that is the division of n. Oh, that was not right using n there. The highest order of 2 dividing n is iron order unity, so n squared, then a is iron order 2. So x let's say it has a factor of 2 to b. Now, how is it? If they are equal, it can be any factor higher if the factors a and b are equal, and if they're different, it's the smallest of them that counts. So we have to work on different values for a and b. So now, first assume a equals naught, meaning that n is odd. And then we have 2b dividing x. That means that x squared minus n squared is odd, or 2 doesn't divide it. Here I'm actually using the, what is it called? Is it the order of the, the order of 2 occurring in the prime expansion of a rational number. So that is actually not quite simple. So maybe it would be more clear if we multiplied. Oh, but then we can't use the n being square free if we multiply with the common denominator. That'll be complicated at least. So let's just go on as I'm working. You know what? I'll find the correct. I'll just. This is the book, and here it defines the. It's on the left side. So there we've got it. The absolute value is 2 minus the number of times prime factor occurs in the rational number. And then on this page, on the top of the page, it defines the valuation, the p-adic evaluation, as minus the logarithm. And that's, of course, logarithm, the prime logarithm. So it's just the valuation just gives the number of times p occurs in the rational number, with the numerator counted positive and the denominator counted negative. So the valuation, the 2 valuation. Now, Now, if n is odd and x is even, then this is odd. So this has the power 2 to the bth, and that means that some power of 2 occurs here. Now, this was odd, so we will have an even denominator. Now, be larger than the naught. Now, if x is odd as also, then x squared minus n squared can certainly be even. It will be even, they are both odd, meaning y will be even, but then this can have a rather large factor of 2. Actually, any factor. So let's say 2 to the cth. Oh, how much will we have of y here? Because that's x. So if we subtract 2n squared, then we have subtracted 2n squared, and n is odd, so that has 2 to the first power. So if c is 1, it becomes complicated pretty quickly. So let's do c equals 1 first. Then x minus n squared is even. So this is even, so y is even. My God, what am I doing here? They may have 2 in the denominator or in the numerator, and I'm thinking as if we are dealing with integers here. Maybe we should go by it a totally different way and reducing this via this equation and introducing y and then also x up here. Because I feel this is not really bringing me anywhere. It becomes more and more complicated. So let's see if I can do that. I could eliminate n from the equation. I'm not sure that would help. Then I could get x squared. Could do away with x squared up here. That would introduce x and some more y. Let's try that. Just becomes more complicated, does it? Oh, here we have if y. Now I'm thinking integers again. So if y have a positive factor of 2 in this expression, naught goes as well, then the 2 cancel here. My God, I'm not used to thinking like this with rational numbers. So there's the method here with using the valuation and then thinking about that. So we should end up with the valuation of this expression being negative. And as far as I remember from here, the valuation was the minimal of the two. The valuation of the sum is larger than or equal to the minimum. And that's not nice because we need to show it's negative. So using the valuations as I was about doing here is maybe not really the point. All right, it's time for another break. I hope I can finish it today though. So the day is coming to an end. I worked a little on the valuations and it seemed to get me nowhere. So well, it's becoming dark outside. I'll just turn off my light so you can see it's actually dark outside now, or dusk. So we'll wait till another day. Hello there. Back again. I believe that I solved problem 2C, problem 2C yesterday, and today I'm ready to make the video. But this is actually the second take, because I made a terrible mistake with the first take. We have the x value of 2p from the first page, and then I made this simple transformation, and I believe you can see the error straight ahead. This is y squared. So so everything was wrong. So we'll just do it from the top down. Now, I have here the information on the valuations which we will be using. I stated it. Now, what was that? I stated it very shortly in the last video, but I just wanted to do it properly. So it's called valuations, and you can study them from this reference, PM Cone, algebraic numbers and algebraic functions, should you wish to. It's a very good algebra book. It's very abstract, but very useful. So now, for a rational number x, we take out the powers of 2 from the numerator and denominator, and write it as a power of 2. And then the 2 value of x is set to the power of 2 that comes out, and naught is assigned to infinity. With this, it satisfies the logarithmic law, and the sum is larger than or equal to the minimal valuation of the 2. That's obvious. A factor 2 you can set out to take out from both x and y. That will go outside the parenthesis, giving this relation. And if they have different valuations, then you can take the least power outside and then get an odd and an even number being added. So that leads to this guy. That it's actually equal, the valuation of the sum is actually equal to the least of the 2 valuations. So that was the theory. Now back to what I did here. So the first mistake is already here, and then I worked on this wrong. So now maybe it would be better to delete it all and start from the top. There we go. So this is more right, and one can also check the dimensions, which I failed to do. I realized when I was halfway through the video, thought I was finished, that the dimensions didn't fit. This is length to the x is length to the 2nd, 4th, length to the 8th, divided by length to the 6th. That gives length squared, which is exactly the x value. So, taking the valuation of this leads to the x value of 2p twice the valuation of x squared plus n squared minus 2. It's the valuation with respect to the prime 2. We don't write that. Minus the valuation of x minus the valuation of x squared minus n squared. This needs to be negative. But actually, since it's a square, it must be less than or equal to minus 2. So that means that the rest must be non-positive. And my problem here is that if we if we know v of x, the value of x, then if it's the same as n, there's no limit to how large this can be, or this, but they're not coordinated in any way. So it was very difficult to put a limit on this. But then I got an idea, and that was that this is not just the sum of two numbers, it's the sum of two squares. So using the sum of two numbers doesn't really cut it. It's the number of two squares and the sum of two squares. And it's only if they have the same. So we write x equals 2 to the nth a divided by b, and y 2 to the nth c divided by d. And what I realized was that this being the numerator being sum of two squares, gave us some information. We know that A, D, B, and C are odd. So this is the square of an odd number. This is the square of an odd number. So if we work modulo 4, this is 1 modulus 4, and this is equivalent to 1 modulo 4. So the sum is equivalent to 2 modulo 4. So that means it's even all right, but the valuation of this sum is 1. And that gives us the formula. And it only holds, of course, for p equals prime p equals 2. So this is exact. It was quite surprising. And doing the same thing, you get that it's larger than or equal to 2n plus 2. We will later improve upon the last inequality, but that's what I was working on. So now we have to work on this guy, and the relationship between the valuation of x and n is crucial. So we make one where the value of x is larger than the value of n. That's an A. And v of n may be either naught or unity because n is square free. Now S equals 2 times x squared plus n squared. That's the minimum of them, and that's 2v of n. Minus v of x minus, and this guy is larger than or equal to, no, that's the same. It's 2 times vn. So we get 4 minus 1 is 3v, 4vn minus vn minus 2n equals, it's 2vn minus v of x. And vn is either naught nor unity, so vx is at least one larger than that. That's 1.12. So we get minus 1 and naught. So in this case, depending on whether n is odd or even, we get that it's equal to naught or minus 1. That was A. Then let's take C. V of x is less than v of n. That's 2v of x. Now that's v of squared, so it's 4 times. As before. And this is twice v of x. And that gives v of x. But v of x being smaller than v of n means it's smaller than 1. So it's smaller than or equal to 0, as it must be. So that was easy. So the last case that they are equal remains. Now we had very nice value for the sum here, which I'll just have to find. So the sum, that's 2 times, it's the same one. 2 times x plus 1. 2 times the value of them times 1. So let's call this n. 2n minus, isn't it plus 1? Should be plus 1. 2n plus 1, yes? Minus n. And then this one was larger than 2n plus 1. So that means that s is smaller than. So this gives minus n. And v of n, that's less than or equal to 0. That's interesting, because when I did this the first time, I didn't get it quite below 0. Not so easy. I had to think some more about it. Just show the result, because it's interesting in its own right, even if one doesn't need it here. So I was looking at this example with n equals 6 and the point minus 2 point. I don't remember, it's 8 or 9 or plus minus, whatever. That doesn't matter here. So and then I looked at this guy, which I wanted to be greater than 3 that we already know it will give. So I computed, of course, the sum equals 4. That's 2n plus 1 that we already have. But 4 minus 36, that gave minus 32, which has valuation of 5. So are we just lucky here, or is there some method to it? And then I realized, oh my God. When we get a minus here, then if we work modulo 8, then this is equivalent to 1 modulo 8. This is equivalent to 1 modulo 8. So modulo 8, the odd numbers are plus minus 1, plus minus 3. And if we square it, then we get plus 1 modulo 8. It's 1 or 9, so it's 1 modulo 8. Modulo 8. So that means that the difference, if we subtract them, so if there's a minus here, oh, that should have been outside too, then it's 0 modulo 8, and that means that it's actually larger than 2n plus 3, not plus 1. It's not just even, it's actually much more even. So it's plus 3. So that was I think that was a nice result. And of course it only holds when the prime is 2. So be careful. But we seem not to need it here, which is a bit odd, but never mind. Let's stop here and then say that I've solved the problem. Not one of my best videos, I think, but in the end I got through it.